All right, so this is another Lagrangian example, problem 7.3 out of Taylor. So it says, consider a mass m moving in 2 dimensions with potential energy equal to 1/2 kr squared, where r squared is x squared plus y squared. Write down the Lagrangian using the x and y, and find the 2 Lagrangian equations of motion. Describe their solutions. This is the potential energy of an ion in an ion trap. So that's just fun information. But actually, let's go through and solve the problem. So the positions, we'll say x is equal to x, y is equal to y. They want the Lagrangian using x and y coordinates. So we need the position first, and then we need the velocities, which is just the time derivative of position. So this is 1, this is 2, 3 is to find your kinetic energy. So T is equal to 1/2 mv squared, or 1/2 m x dot squared plus y dot squared. And then we need the potential energy. Now the potential energy, they said, was U is equal to 1/2 kr squared, which is just 1/2 k x squared plus y squared, since they tell us what r squared is equal to. And then after you do these 4 steps, you can write down the Lagrangian, which is part of the problem. The Lagrangian is just kinetic minus potential. So I'm just going to plug in what we found earlier. So this would say is step 5. And then step 6 is the Euler Lagrangian. I'm just going to write this in general terms. The Q can be any coordinate. It could be x and y. In this case, we want it x and y motion. So we're going to break this up into essentially 2 problems. X motion and y motion. And they're going to look pretty identical, just like we would do if we were doing Newton's second law, right? Because they're vectors, we'd often break them up into components. This really isn't much different in the sense that we have to break it up into x and y motion. So for the x, we could say dl dx minus d by dt, your partial of L with respect to x dot equal to 0. And we can use the part 5 to just take some derivatives. So dl by dx is just going to be minus kx minus d by dt. If we take the time derivative, we'll just get mx dot equals 0, or minus kx minus x double dot, because we take the time derivative, is equal to 0. Mx double dot equals negative kx. And solving for x dot, we have minus k over m x. And we can do the exact same thing with the y direction. And you'll see it's essentially the same idea, except instead of x's, we get y's. So minus ky, just skipping ahead here, my double dot equals negative ky. Y double dot is negative k over my. Okay. And that's all we have to do for this problem. If you wanted to, we've done this before. In fact, in the previous problem, we gave a general solution to this differential equation. So if you want the actual x of t, y of t, then you can look back on that. But this is really all the, I guess you could say, meat of the